After we have already looked at the basics of state space representations in chapter 9, in this chapter we will look at the basic concept of stability. As before, we will equally cover the discrete time case and the continuous time case. And here we start with the case of a discrete time LTI state space model, which was introduced in chapter 9 and which is stated here again in equation 26, including the system equation and the output equation. In addition to the system, we suppose here that some non-singular matrix T is given. Non-singular means that the rank of the matrix T is equal to its dimension n, and moreover, the columns of T are linearly independent and hence they form a basis for the space Rn. As we know from the change of basis, if x is any vector in the Euclidean basis of Rn, then x tilde, which is defined as follows, is the corresponding representation of x in the basis B tilde, which is defined by the columns of the matrix T. Namely, x tilde is defined in such a way that if T is multiplied with x tilde, we get the vector x. And that's because from the basic mechanics of matrix vector multiplication, each entry of the vector x tilde multiplies the corresponding column vector in the matrix T in order to obtain the vector x. Since the matrix T is invertible, we can also express this equation by writing x tilde is equal to T inverse times x. With this matrix T, which we also call a transformation matrix, we now modify our state space model in equation 26 as follows. First, we multiply the state equation 26a from the left with T inverse, which leads to a factor of T inverse in front of each term of the state equation and also of the initial condition. And second, we insert the identity matrix, which can be written as T times T inverse, once in the state equation and once in the output equation. Note that this allows us to define a new state space representation in terms of the transformed state x tilde, which is defined as T inverse times x, where x tilde appears at this point and at this point in the state space representation, and this expression here is equal to x tilde of k plus 1, and also the initial condition is transformed such that we now have an expression for x tilde of k naught. Moreover, the system matrix of the transformed system, which we call A tilde, is given by the expression T inverse times A times T. The input matrix of the transformed system, which we call B tilde, is given by T inverse times B. The output matrix of the transformed system, which we call C tilde, is given by C times T, and the throughput matrix of the transformed system, D tilde, is given by D. Observe that the input-output behavior of the transformed system is exactly the same as the one of the original system, meaning that if we put in the same inputs u of k, we will get out exactly the same outputs y of k without the need to do any transformations of the inputs or outputs. The only thing that needs transformation is, of course, the initial condition in terms of the initial state of the system. This entire process is called a similarity transformation of the state space model, and it's specified in definition 12.1. So let T be any non-singular matrix, then the corresponding transformation of the discrete-time LTI state space model 26 into this state space model, which we have just defined on the previous slide, is called a similarity transformation. the inputs and outputs of the transformed system remain the same as those of the original system, and the only thing that's transformed is the state vector, which is now called x tilde, and it's defined by t inverse times x, and it can be interpreted as a change of basis from the Euclidean basis into the basis that's given by the column vectors of the transformation matrix T. And finally, the system, input, output, and throughput matrix of the transformed system are given by the formulas that have been derived on the previous slide. Hence, the statement of proposition 12.2 has already been proved, namely the input-output behavior of the transformed system, 27, is the same as that of the original state space model, 26, and for all times k greater than or equal to the initial time k0, we have that the states of the original system and those of the transformed system are related by this transformation equation. So far, we have not talked about the selection of the transformation matrix T. In principle, the formulas for the similarity transformation work for any selection of T. However, there are a small number of transformation matrices which are of particular importance. The first one is stated in definition 12.3, where the transformation matrix T is selected as the transformation matrix of the Jordan form of the system matrix A. And if this particular transformation matrix is selected, then the corresponding similarity transform is called the Jordan canonical form of the original state space model in 26. So what are the consequences of selecting this particular transformation matrix T? By looking at the formula for the transformed system matrix A tilde, we see that it takes on the Jordan form of the original system matrix A, which means that if A is a simple or at least semi-simple matrix, then A tilde will have this diagonal form with the eigenvalues of A on its diagonal. If A is not simple, or at least semi-simple, then A tilde may have, in addition, some entries of 1 on its superdiagonal. As opposed to the system matrix, the input, output, and throughput matrix of the Jordan canonical form will have no special structure. After introducing similarity transformations and the Jordan canonical form, which we will need later on for stability proofs, we now turn our attention to different concepts of stability. For these notions of stability, we will first restrict ourselves to discrete-time linear autonomous systems. In fact, the notions of stability that we will look at in just a moment can be generalized to discrete-time nonlinear autonomous systems, where the state equation is given by equation 28. Here, the state at the next time step, x of k plus 1, is given as some nonlinear function of the state at the current time step, x of k, and the time k. And of course, this nonlinear system also starts from some initial condition x0. Clearly, this nonlinear autonomous system is a generalization of a linear autonomous system where the function f is given by a matrix A of k times the current state x of k. Now, definition 12.4 defines the concept of an equilibrium point of a discrete-time nonlinear autonomous system, and that's a point x bar in the state space, which satisfies the condition that x bar is equal to f of x bar and k for all times k. Now, why do we need this definition of an equilibrium in the context of stability? That's because stability always refers to an equilibrium point and not the entire system. For linear systems, however, note that the origin is always an equilibrium point. And that's because if you look at the system equation, x of k plus 1 is equal to a of k times x of k, you see that no matter what a of k is, since it's a matrix, it follows that a of k times 0 is always equal to 0. Now, definition 12.5 states that any equilibrium x bar of a discrete-time autonomous system is said to be stable in the sense of Lyapunov, or simply stable if for every time step k0 and every positive epsilon there exists a delta which depends on this k0 and the epsilon, such that if the initial condition x of k0 is delta close to the equilibrium point x bar, then the entire state trajectory will remain epsilon close to the equilibrium point x bar for all times k greater than or equal to k0. For an illustration of this definition, suppose that any initial time step k0 and any positive epsilon are given, and let x bar be our equilibrium point, and the red circle here represents our epsilon ball, which is centered at x bar. Then what we need to show in order for x bar to be stable in the sense of Lyapunov is the following. It must be possible to find a value of delta such that if the initial condition of the system starts anywhere in a delta ball centered at x bar, then the state trajectory starting at x of k0 will remain inside the epsilon ball for all times k greater than or equal to k0. And this must work for any initial condition inside this delta ball, that the state trajectory may actually leave the delta ball, but it may never leave the epsilon ball. In the following, when we use the term stable, we will always mean stable in the sense of Lyapunov, unless stated otherwise. For linear systems, which is of course the main subject of this course, we implicitly assume that the origin is the relevant equilibrium point. Therefore, we often colloquially refer to a linear system as a stable linear system, and what we mean by this is that the origin is stable in the sense of Lyapunov. And linear systems that are not stable, so where the origin is not stable in the sense of Lyapunov, will be called unstable. A stronger notion of the stability of definition 12.5 is global stability, which is defined in definition 12.6. In fact, an equilibrium point x bar is said to be globally stable if the delta in definition 12.5 can be made arbitrarily large for sufficiently large epsilon. In other words, if x bar is globally stable, then the stability condition holds, and in addition to that, if epsilon goes to infinity, it's also possible to let delta go to infinity. From definitions 12.5 and 12.6, it's very important to understand that stability or global stability do not imply that the state trajectory converges to the equilibrium x bar as k goes to infinity. All it says is that if the initial condition starts close enough to the equilibrium point x bar, then the system trajectory will remain somewhat close to the equilibrium point x bar at all times in the future. In case of stability, that works in some neighborhood of x bar, and in case of global stability, that works in the entire state space. In order for the system trajectory to converge to the equilibrium as time goes to infinity, we actually need stronger notions of stability. These stronger notions, called asymptotic stability and exponential stability, are specified in definition 12.7. In fact, an equilibrium x bar of a discrete-time autonomous system is called A, exponentially stable, if it is stable and in addition there exists a delta bar such that the limit as time goes to infinity of the norm of the difference between x of k and x bar is equal to 0, which means that the state x of k converges to x bar, and that must hold for all initial conditions x of k naught that are within a delta bar ball of x bar. Moreover, the equilibrium x bar is called B exponentially stable if there exists a delta bar such that this condition is satisfied for all initial conditions x of k naught inside a delta bar ball of x bar. Now let's take a closer look at this condition. It contains two constants. One is called c and it's positive, and one is called beta and it's positive but strictly less than 1. The condition is saying that the distance between the state x of k and the equilibrium x bar is less than the initial distance between the state x of k naught and x bar multiplied by a constant and multiplied by a factor beta, which is less than 1, to the power of k minus k naught. So as k increases, this term will get smaller and smaller. In fact, it will get exponentially smaller. That's why the stability notion is called exponentially stable. And hence, x of k has to get exponentially closer to the equilibrium point x bar. Again, we can extend these stability notions to be called globally asymptotically stable and globally exponentially stable if the respective conditions hold for all initial states x of k naught, or in other words, if the delta bar of k naught is equal to infinity. Proposition 12.9 states that A, exponential stability, is a stronger notion than asymptotic stability, or in other words, if an equilibrium is exponentially stable, then it is asymptotically stable, and B, that asymptotic stability is a stronger notion than stability, or in other words, if an equilibrium is asymptotically stable, then it is stable in the sense of Lyapunov. For the sake of getting a little more familiar with these stability concepts, we will now prove proposition 12.9. For part A, we want to show that if the system is exponentially stable, then it is asymptotically stable. So let x of k denote the state trajectory that starts from any initial state x bar of k naught, which lies inside a delta bar ball centered at the equilibrium x bar. By assumption, the system is exponentially stable, hence there exist two constants, c, which is positive, and beta, which is positive and strictly less than 1, such that the condition for exponential stability is satisfied. In the rest of this proof, we will refer to this condition as the equation star. In order to prove asymptotic stability, according to definition 12.7a, we have to show two things. First, stability of the equilibrium x bar. To do this, we suppose that any positive value of epsilon is given to us, and we pick the corresponding delta of k naught and epsilon as the minimum of two values, namely epsilon divided by c of k naught and delta bar of k naught. Then, with star, it follows that the norm of x of k minus x bar is less than c times the norm of x of k naught minus x bar times beta to the power k minus k naught, where now, by assumption, the initial state x of k naught is in a delta ball around x bar, and with our particular choice of delta, this norm is less than epsilon divided by c of k naught. Therefore, the whole thing is less than c times epsilon divided by c times beta to the k minus k naught. Of course, the c cancels here, and since beta is less than 1, beta to the k minus k naught is less than or equal to 1 for all k greater than or equal to k naught. Hence, we can conclude that the norm of x of k minus x bar is less than epsilon for all k greater than or equal to k naught, which is exactly what we wanted to show in order to prove stability. The second thing we need to prove for asymptotic stability is convergence of the state trajectory x of k to the equilibrium point. Based on the assumption of equation star, this is easy to see because the first two factors are actually constants in k, and this term beta to the power k minus k naught is actually shrinking exponentially as k increases, and therefore it's clear that as k goes to infinity, the norm of x of k minus x bar has to go to 0. Part B of this proposition is trivial because by definition 12.7a, asymptotic stability already implies stability. Now that we have seen that exponential stability is stronger than asymptotic stability, and asymptotic stability is stronger than stability, let's look at some examples to prove that in both cases stronger means strictly stronger. So in case A, that there are systems which are stable but not asymptotically stable. An example of such a system can be found here. And in case B, that there are systems which are asymptotically stable but not exponentially stable. And an example of such a system is given here. Let's prove these claims for our two examples. In case A, for the stable but not asymptotically stable system, note that if we pick any non-zero initial condition x of k naught, which is equal to some vector consisting of the components a and b, we obtain by using the state equation that x of k naught plus 1 is equal to minus ba, x of k naught plus 2 is equal to minus a minus b, x of k naught plus 3 is equal to b and minus a, and x of k naught plus 4 is again equal to a and b, and so on. Now we see that if the initial condition is close to the origin, so a and b are small, then the entire state trajectory will stay close to the origin for all times k, but it will never converge to the origin. In case B, let's prove that this system is asymptotically stable but not exponentially stable. To this end, pick again any initial condition x of k naught equal to a, and then observe that x of k naught plus 1 is given by k naught plus 1 divided by k naught plus 2 times a. X of k naught plus 2 is then given by x of k naught plus 2 divided by k naught plus 3 times x of k naught plus 1, where we can now substitute x of k0 plus 1, and the k0 plus 2 cancels out, and we obtain that x of k0 plus 2 is equal to k0 plus 1 divided by k0 plus 3 times a. Similarly, we obtain x of k0 plus 3 equal to k0 plus 1 divided by k0 plus 4 times a, and so on. From this, it's easy to see the general formula for x of k, which is equal to k0 plus 1 divided by k plus 1 times a. From this, it immediately follows that no matter the value of a, the limit of the norm of x of k as k goes to infinity will be 0. So the system is globally asymptotically stable. Now, for the sake of a contradiction, assume that the system is also exponentially stable. Then there must exist two constants, a positive c of 0 and a beta of 0, which is positive and less than 1, such that this condition is satisfied. Note that without loss of generality, we have chosen k0 to be equal to 0 here, and the relevant equilibrium point x bar is the origin anyways, since we're dealing with a linear system. Since x of k is given by 1 over k plus 1 times a, and x of 0 is given by a, we obtain this inequality where we can cancel the absolute value of a on both sides, and hence, solving for the constant c of 0, we obtain that 1 over c of 0 must be less than, in brackets, k plus 1 times beta of 0 to the power k. This condition, however, must hold for all k greater than or equal to 0, and this is not possible because the right-hand side converges to 0 as k goes to infinity. To see this, note that k plus 1 in brackets times beta to the power k can be written as beta to the power of the logarithm with respect to the basis beta of k plus 1 plus k, where beta is some number less than 1, and the exponent, which is the logarithm with respect to the basis beta of k plus 1 plus k, goes to infinity as k goes to infinity, and hence the limit of the whole expression tends to 0. Hence, we have established a contradiction, and the system under consideration cannot be exponentially stable. After we have introduced all of these stability concepts, stability in the sense of Lyapunov, asymptotic stability, and exponential stability, and all of them holding locally or globally, we now have a fact in 12.10 that relates the stability of a similarity transform to the stability of the original state space model. And in fact, what it says is that the similarity transform has exactly the same stability properties as the corresponding original state space model for any non-singular transformation matrix T. For the proof of fact 12.10, note that by proposition 12.2, x of k is equal to t times x tilde of k for all k, and since t is invertible, we also have that x tilde of k is equal to t inverse times x of k for all k. With proposition 11.7, for the induced norm of the linear maps T and T inverse, it follows from the first equation that the norm of x of k is less than or equal to the induced norm of T times the norm of x tilde of k for all k greater than or equal to k0. And from the second equation, it follows that the norm of x tilde of k is less than or equal to the induced norm of T inverse times the norm of x of k for all k greater than or equal to k0. Now, in both cases, the induced norm of T and T inverse is a finite number which does not depend on k. Therefore, the result of fact 12.10 follows with the observation that all stability definitions are not affected by a constant factor. The final stability concept that we define for discrete time systems is uniform stability. And according to definition 12.11, all the stability notions of definitions 12.5 to 12.8 are called uniform if the conditions stated in these definitions are independent of the initial time k0. Specifically, this means that the equilibrium x bar of a discrete time autonomous system is called uniformly stable if the delta in definition 12.5 is independent of k0. A system is called uniformly asymptotically stable if in definition 12.7a the word stable is replaced with uniformly stable and the expression delta bar of k0 is replaced with just delta bar. A system is called uniformly exponentially stable if in definition 12.7b the delta bar of k0, the c of k0, and the beta of k0 are independent of the time k0. Clearly, uniform stability implies non-uniform stability, but not vice versa. Moreover, for time-invariant systems, non-uniform stability implies uniform stability. Theorem 12.12 states our main stability result for discrete time, linear time invariant autonomous systems. In fact, for a discrete time, linear time invariant autonomous system with the general state equation given by this equation, where lambda 1 through lambda n represent the eigenvalues of the system matrix A, there are only three possibilities for the stability of this system. A, the system can be globally uniformly exponentially stable, and that's the case if and only if all of the eigenvalues are in absolute value less than 1. The second possibility, B, is that the system is globally uniformly stable, and that's the case if and only if all of the eigenvalues are less than or equal to 1, and for any eigenvalue lambda I which is in magnitude equal to 1 and which is repeated mi times, it holds that the nullity of lambda I minus a must be equal to mi. And finally, the third possibility is that such a system is unstable, and that's the case if and only if there exists an eigenvalue lambda I which in magnitude is greater than 1, or there exists an eigenvalue lambda I with magnitude equal to 1 that is repeated mi times, and it holds that the nullity of lambda I minus a is less than mi. In order to avoid any complications which are not insightful, in the proof of Theorem 12.12, we restrict ourselves to the case where the matrix A is either simple or at least semi-simple. Now, if A is simple, this means that A has n distinct eigenvalues lambda I, or in other words, every eigenvalue lambda I is repeated exactly one time. Moreover, we have the convenient fact that for each eigenvalue lambda I, there exists an eigenvector xi with the property that a times xi is equal to lambda I times xi. And thus, we have that in brackets lambda I times identity minus a times xi is equal to 0. And since xi is the only vector for which this is true, this implies that the null space of the matrix lambda I times identity minus a is equal to the span of xi, and hence the nullity of the matrix lambda I times identity minus A is equal to 1. In the other case, where A is semi-simple, the eigenvalues lambda I can be repeated more than one time. In fact, they can be repeated mi times, but there must exist mi linearly independent eigenvectors in this case, which we call xi1 through xi-mi, so that the null space of lambda I times identity minus A is given by the span of these eigenvectors, and hence the nullity of the matrix lambda I minus A is equal to mi. What you can see from this is that basically all of the cases mentioned in Theorem 12.12 can appear, except for the last case in part C, where an eigenvalue is repeated mi times, but the nullity of the matrix lambda I times identity minus A is less than mi. By fact 12.10, the discrete-time LTI autonomous system has the same stability properties as its Jordan canonical form, which looks like this for the transformed state x tilde of k, whose initial condition is given by T inverse of x naught. Note that the system matrix lambda is diagonal in the case where A is simple or semi-simple, and it carries the eigenvalues of A on its diagonal. According to Theorem 9.23, the state trajectory of the Jordan canonical form is given by x tilde of k is equal to the matrix lambda to the power k times the initial condition x tilde of 0. Since lambda is a diagonal matrix, we can also express lambda to the power k as the diagonal matrix which has all the eigenvalues lambda 1 through lambda n to the power k on its diagonal, and multiplying this diagonal matrix with the initial condition, which yields the vector lambda 1 to the power k times x tilde 1 of 0, lambda 2 to the power k times x tilde 2 of 0, and so on down to lambda n to the power k times x tilde n of 0. Hence, the Jordan canonical form is clearly A, globally exponentially stable if and only if all eigenvalues lambda I are in magnitude less than 1. B, globally stable if and only if all of the eigenvalues are in magnitude less than or equal to 1. And remember that in this case, any repeated eigenvalue with magnitude 1, which is repeated mi times, satisfies that the nullity of lambda I times identity minus A is equal to mi. And C, unstable, if and only if there exists an eigenvalue lambda I, which in magnitude is greater than 1. And as a final remark, note that any stability property will automatically be uniform since we're dealing with a time-invariant system. On the next couple of slides, we will transfer the same concepts that we have defined for discrete time systems to continuous time systems. The whole thing is pretty much analogous, and therefore we go through this fairly quickly. First, we can define similarity transformations analogously for continuous time systems, where T is again a non-singular matrix with rank of T being equal to n, and the columns of T form a basis B tilde for the space Rn. Hence, if X is a state vector in the original Euclidean basis, then X tilde can be interpreted as a representation of X in the basis B tilde. So X is defined as T times X tilde, and hence we can also write X tilde as T inverse times X. then we do the same tricks as before, namely multiplying the state equation from the left with T inverse and also the initial condition, and inserting T times T inverse in two places of the state and the output equation. This so-called similarity transformation is summarized for the continuous time case in definition 12.13. Here T is some non-singular matrix, and the corresponding transformation of the continuous time linear time invariant state space model into this continuous time linear time invariant state space model is called a similarity transformation. The transformed state vector x tilde, which is defined as T inverse times x, emerges from a change of basis of the Euclidean basis of the vector x into the columns of T. The system input, output, and throughput matrix of the similarity transform are given by these formulas, which are exactly the same formulas as for the discrete time case. Again, the similarity transform in equation 30 has exactly the same input-output behavior as the original state space model in equation 29. And moreover, for all times t greater than the initial time t0, we have that the state x of t is given by t times the transformed state x tilde of t. As before, the Jordan canonical form of a continuous time linear time invariant state space model is a particular similarity transform of the original system, where the transformation matrix T is equal to that of the Jordan form of the system matrix A. This implies, of course, that the transformed system matrix A tilde will be in its Jordan form, meaning that it will be diagonal if the matrix A is simple or semi-simple, or otherwise it may have entries of 1 along its superdiagonal. As for the discrete time case, we can now define different notions of stability for continuous time linear autonomous systems, which can actually be extended also to continuous time nonlinear autonomous systems. The state equation of a continuous time nonlinear autonomous system is given by the time derivative x dot of the state vector being equal to some nonlinear function f of the current state x of t and of time. In the case of continuous time systems, a point x bar in the state space is called an equilibrium point of the nonlinear autonomous system 31 if it satisfies the condition that f of x bar and t is 0 for all times t. And that's because in the continuous time case, this implies that the derivative of the state x dot is equal to 0, and hence the state will stay at this equilibrium point for all times t. Again, as before, stability always refers to an equilibrium point x bar and not the entire system. However, for linear systems, the origin is always an equilibrium point. And moreover, whenever we're dealing with a linear system, unless stated otherwise, the origin is implicitly assumed as the relevant equilibrium point. We can analogously define stability in the sense of Lyapunov for the equilibrium of a continuous time autonomous system by demanding that for every time t0 and every epsilon which is positive, there must exist a delta which depends on t0 and epsilon such that if the trajectory starts within a delta ball around x bar, then it will remain inside an epsilon ball around x bar for all times t greater than or equal to t0. The stability is called global if this delta can be made arbitrarily large for sufficiently large values of epsilon. Moreover, the equilibrium is called asymptotically stable if, in addition to being stable, we have that the state trajectory converges to the equilibrium as time goes to infinity for all initial conditions in some delta bar ball of x bar. It is called exponentially stable if this exponential stability condition is satisfied for all initial conditions in a delta bar ball around x bar, where c and alpha are two positive constants. The two stability definitions in A and B are again called global if x bar is globally stable and the respective conditions above hold for all initial conditions x in Rn, or one could say that delta bar has to be infinity. Now, proposition 12.19 states that also for continuous time systems, we have that A, if an equilibrium is exponentially stable, then it is asymptotically stable, and B, if an equilibrium is asymptotically stable, then it is stable. And the proof is analogous to the proof of proposition 12.9. Here we have two examples of A stable but not asymptotically stable continuous time system, and B, an asymptotically stable but not exponentially stable continuous time system. And it will be on you in exercise 13.1 to prove the stability properties for these two examples. Fact 12.20 states that also for the continuous time case, a similarity transform has the same stability properties as the corresponding state space model, and that's for any non-singular transformation matrix T. The proof of this fact is again analogous to the discrete time case, which we have proved in fact 12.10. All stability notions introduced in definition 12.17 and definition 12.18 are called uniform if they are independent of the initial time t0. In other words, the equilibrium x bar of a continuous time system is uniformly stable if the delta of t0 and epsilon in definition 12.17 does not depend on t0. It is called uniformly asymptotically stable if in definition 12.18a stable is replaced with uniformly stable and the delta bar of t0 is a constant delta bar. It is called uniformly exponentially stable if in definition 12.18b the values of delta bar of t0, c of t0 and alpha of t0 are independent of the initial time t0. Clearly, uniform stability always implies non-uniform stability, but not vice versa. However, for time-invariant systems, non-uniform stability implies uniform stability. Now, Theorem 12.22 summarizes the main stability results for a continuous time, linear time invariant autonomous system of this form, where lambda 1 through lambda n denote the eigenvalues of the system matrix A. Now, the stability of such a system can only fall into one of three cases. The first case being A, it is globally exponentially stable, and that's the case if the real part of all eigenvalues is strictly negative. B, it is globally stable if the real part of all eigenvalues is non-positive, and moreover, for any eigenvalue lambda I whose real part is equal to 0 and which is repeated mi times, it must hold that the nullity of the matrix lambda I times identity minus A is equal to mi, and C, it is unstable if either there exists an eigenvalue with a real part that is positive, or there exists an eigenvalue lambda I with a real part that is 0, and that is repeated mi times, and it holds that the nullity of the matrix lambda I times identity minus A is less than mi. And the proof is again similar to the proof for the discrete time case in Theorem 12.12 and therefore omitted.